In this video, we'll discuss the ANOVA table for regression specifically. Now, in previous classes, I'm sure you've seen a traditional ANOVA table. As a reminder, ANOVA stands for Analysis of Variance, and in an ANOVA table, we partition, which means split apart, sources of variation. Now, in an ANOVA table for regression specifically, we look primarily at two sources of variation. We look at sources of variation from the model and sources of variation from error. This is certainly not the only way in which you can look at ANOVA, and sometimes we can break the sources of variation down by independent variable if we have multiple, and use partial sources of variation and other different tools to approach trying to break down where variance in the data is coming from. But ultimately, the goal is to break down how our outcome is changing and which components are most associated with changes in the outcome. So typically what we do to look at sources of variation is we use the sums of squares. So the sums of squares tends to be this source of variability that we use, and then we break down those components even further. So the big one that we start with is the total sums of squares, sometimes called SST or SS sub t. The total sums of squares is just the sum of y minus y bar quantity squared. This is the sums of squares in the outcome, and this represents a measure of the total variability in the data. This is, in some way of thinking, all of the movement in the data. Our goal is to explain this movement with our independent variables, and if our independent variables explain a meaningful proportion of this, we can call it statistically significant. A non-zero proportion of this, or we have evidence that it explains a non-zero proportion of this in the population, we call it statistically significant. Now the percentage of this that we explain is called the coefficient of determination, or R squared. So another thing that we'll discuss in this lecture series is the concept of R squared within the regression model. And actually, now that we're talking about sums of squares, we can start to approach this. That is that R squared is the percentage of the sums of squares total that we explain from our model. Now again, the model we're going to split into two different parts of variation. The total variance we're going to split into two different parts of variation: the model variation and the error variation. So if we're looking at something like this, actually this mathematically makes sense. If we have y sub I, and this equals, if we have, y sub I minus y bar. Here we have y sub I minus y bar, and then we have a positive y hat and a negative y hat, so these two cancel each other out. The reason we write it in this way is because this explains the partition. When we add in the y hats, this explains the partition that we're looking at. The difference between y hat and y bar, this is the partition piece that has to do with regression, and the difference between y and y hat, if you remember, this was the definition of our error term as y minus y hat. Now what's interesting is that we can start from this equation, which is mathematically correct, even at face value. Again, y minus addition, we can rearrange outside of the parentheses, so y minus y hat is 0. This leaves us with a negative y bar plus y, and again we have y minus y bar, so the left and right would be the same. But the interesting thing is that this not only is true for an individual data point, but that from the sum perspective, this is also true. So the sum of squares of y minus y bar is equal to the sum of squares of y hat minus y bar plus the sum of squares of y minus y hat. Now this is not trivial. This is a proof you may have on your homework assignment, but this is not a small thing. This is not a given thing. In fact, at face value, this shouldn't necessarily work. We can't just square these specific things. That's not mathematically correct. So there's a bit of proving that has to go in this arrow where we start from here and go down to the bottom. But this is a very, very, very handy result. What this means is that the total variation can be broken down completely into the sums of squares total can be broken down completely into sums of squares coming from the regression and sums of squares coming from the error, and that there's no bits left over. This is a hugely, hugely important concept in regression and in statistics in general, sometimes called the fundamental ANOVA rule. Now, this illustration can be helpful to demonstrate what's going on. So we've got a data point, and the distance from the data point and the red line, this, if you can visualize this, or you want to write it on your notes, is y minus, the red line is y bar. So this is y minus y bar, and that is the total variation. So this vertical line, distance between y and y bar, is the total variation. Now this dashed line up top, so recall that the regression line, the red line is y bar. The regression line here, this regression line is y hat. That's the predicted line. So the distance between y and y hat, well, that's y minus y hat. That is the regression component. Or excuse me, y and y hat. That's the error component. Y minus y hat is what we called error, the distance between our predicted value and the actual value. That's our error. So y minus y hat is the error term. And then the last term that we have is y hat, the line, minus y bar. That's this very, very thinly dotted line here. So y hat minus y bar, this was the sum of squares component due to regression. So we have error and we have regression, and then taking these two together gives the total variability, or y minus y bar. So the sums of squares total is the sums of squares error plus the sums of squares from regression. That's what the previous equation is telling us, and this is a graphical representation of that. Now, if we don't do anything at all, if we do nothing and don't use our independent variable at all, the best guess that we have for a y value, the y value, the predicted y value that gives the smallest amount of error, is y bar. So the sums of squares total is the deviations from that y bar. Oops, I apologize, I have a typo here. This should be minus y bar. So the sums of squares total is the deviations from this particular value. And it's just the sums of squares of y. The degrees of freedom, if we don't have any variables, or we're not using anything to account, we're not using any independent variables, that's what I'm trying to say, is n minus 1, because we are still using the mean to predict what the y values are. So we're still doing that mean calculation, so our degrees of freedom won't be n, it'll be n minus 1. The mean squares total is the sum of squares total divided by little n minus 1, and this happens to be the variance of y. So this is the variance of y in terms of the population variance, if we have all the population values, the sample variance if we're using a sample predictor. However, when we add in x, that is when we start to take advantage of a regression model framework that utilizes independent variables, now we have some more components to consider. The sum of squares regression is the distance, as we already talked about, between the predicted value and the mean. Now we're just adding one estimate. Be careful here. We are estimating two values. We're estimating the mean, which is the intercept, and we're estimating the slope. But when we're adding regression to the previous framework from the sums of squares total, we're just adding a single estimator, that is the estimator of the slope, because again, the intercept's already been taken care of. The mean squares of regression is the sum of squares regression divided by the degrees of freedom regression, which again, in this case, when we're just adding a single parameter, is going to be 1. Note that if we had multiple independent variables, this degrees of freedom will change. Now the error sums of squares, this is what's not explained. So this is the distance between what's observed and what was predicted. This is unexplained variation. This degrees of freedom is the difference between the total and the model degrees of freedom. So the total degrees of freedom when it's n minus 1, and then we subtract out the additional degrees of freedom taken up by the model. In this case, that's 1. So n minus 1 minus 1 gives us n minus 2, and that's the degrees of freedom that we have left over for our sums of squares of error. The mean squared error is calculated simply by dividing the sum of squares error divided by the degrees of freedom for the error. And this is the best way to estimate the variance for y, conditioned on the independent variable. So if we're looking for the variability of y after we've taken into account the independent variable, the MSE is the best way to do that. And again, this is our unexplained variation because this is after we've taken into account the independent variable. All right, drum roll please. We finally get to the ANOVA table. So in an ANOVA table, they tend to be set up into 4. Sometimes you'll have 5 or 6 columns. We'll show one with 6 columns in a bit. But typically 4 columns is a good starting place. Maybe a 5th column with the F statistic value next to it can be handy. But the main 4 columns are the source of variability, the degrees of freedom, the sums of squares, and the mean squares. The regression model has 1 degree of freedom. The sums of squares is the sum of y hat minus y bar quantity squared. And then the mean squared is what we've worked out in the previous slide. Sum of squares regression divided by the degrees of freedom. Error is also just what we had earlier in minus 2 degrees of freedom, sum of y minus y hat quantity squared. And then SSE over DFE is the mean squares error, the MSE. And then for total, we have total of n minus 1 degrees of freedom, sum of y minus y bar quantity squared, and then SST divided by DFT is the mean squares total. This quantity is very often not calculated. We don't really use the mean squares total. We do use the mean squares regression and the mean squares error, so these two tend to be calculated, but this one in the bottom right tends to be left blank on most ANOVA tables, so do take that into account. And this is the way in which we present the variability breakdown of the model. Again, the total sums of squares and the total mean squares gets broken down into these different components that add up to give the total. The total sums of squares add up to give this, the total degrees of freedom add up to give, the model and error degrees of freedom add up to the total degrees of freedom, so they sum down below. Now the mean squares doesn't necessarily work like that, and same thing when we calculate F ratios and other stuff, but we do this for the degrees of freedom and the sum of squares. And again, for the mean squares, I mentioned it doesn't work like that. Again, we normally don't calculate the mean squares total, so that's normally not a component we would even be expected to consider. Now, we've talked about the expected value, but because the y value is a random variable, all of the mean squares which involve y's are also considered random variables. The expected value of the mean squared error is sigma squared, and the expected value of the mean squared regression, so this is just the error variability. The expected value of mean squared regression is error variability, but it's plus additional variability that has to do with the x value. So this last component is the additional variability that has to do with the x value. Note that under the null hypothesis, the expected value of the mean squared error and the expected value of the mean squared regression is going to be the same. What that means is that under the null hypothesis, beta 1 is 0. So if I'm doing a null hypothesis for beta 1, it's going to be beta 1 equal to 0. So 0 times the sum of squares of x is 0, and I'm just left with sigma down here. Under the null hypothesis, these two quantities are both going to be the same. And their ratio, that is, if I do the mean squares regression divided by the mean squares error, if both of these are the same, I'm going to have sigma squared divided by sigma squared. That's just going to be 1. Now this is important because this ratio, mean squares regression divided by mean squares error, is exactly how we construct an ANOVA and F test. So we look at the ratio, and this ratio between mean squares regression and mean squares error is distributed as an F distribution with a significance level of 1 minus alpha with 1 degree of freedom and n minus 2 degrees of freedom. Now this is the degrees of freedom of the numerator. That's the first degrees of freedom, and that's 1. And then the degrees of freedom of the denominator, MSE, that's going to be n minus 2. Under the alternative hypothesis, the mean squares regression, well, beta 1 would actually mean something. Beta 1 is non-zero. So under the null hypothesis, because beta 1 is non-zero, the mean squares regression tends to be larger than the mean squared error, and that would make this test statistic be bigger than 1. Typically, we reject the test statistic if it's bigger than the critical value. Or again, like so many of our statistics, we'll get a p-value. If the p-value is less than alpha, we reject the null. So I promised that I'd show you one table with 6 columns. So this is an R-style ANOVA table. Notice a couple things. First of all, it has 6 columns. It has this F statistic included, and this is how we would calculate the F statistic by hand. And it's got a p-value column where it would indicate the p-value. So this is very common in how you'll see these presented in software. One other thing that you'll note that the R table is different from our initial table in is that the R table does not include a total row. So it doesn't include these total values. It just displays the regression or the model and the error. And I think in R, especially after we add multiple components, what you'll see is that the source will even be broken up by the different independent variables, and then you can combine them down into the larger model component. So this video, we've talked about the ANOVA table, constructing an F-test for the regression model, and the breakdown of the sums of squares. In the next video, we'll move on to the general linear test, nested models, and then some more details about correlation and the coefficient of determination.